programming solves complex problems by remembering past answers, but sometimes you don't need a perfect memory. You just need to know exactly when to quit. We are looking at algorithm number 12 in the design strategies category, backtracking. Imagine asking a computer to search a space of possibilities so massive that the universe would burn out before it could list every single option. These are constraint satisfaction problems. You cannot take a greedy shortcut because a good local choice might ruin your entire setup later. And you cannot rely on brute force exhaustion because the number of combinations scales exponentially with every step you take. To navigate these impossible spaces, we use a strategy that mirrors a very basic survival instinct. We test the waters, and we abandon doomed paths the instant they go wrong. The classic stage for testing this logic is the 8 queens puzzle. Proposed by Max Bezel in 1848 and generalized to larger grids by Franz Knock in 1850, the challenge is simple to understand but mathematically dense. Place 8 queens on a chessboard so no two attack each other. The mathematician Carl Friedrich Gauss tackled this by hand in 1850. He would place a piece, check the attack lines, and advance. The moment he realized he was stuck, he would simply back up and move the previous piece to a new square. This manual trial and error was formalized for machines a century later. The mathematician D.H. Lemur officially coined the term backtrack in the 1950s, and Edsger Dijkstra famously used the 8 queens puzzle to champion structured programming in 1972. Backtracking is a direct translation of a century-old human heuristic into machine logic. It is systematic trial and error. To execute this search, the machine follows a strict repeating cycle. It makes a choice, recurses deeper into the problem, and if it hits a dead end, it undoes that choice and tries the next available alternative. This graphic compares the 2 main search strategies side by side. On the left, brute force blindly builds out every complete candidate, generating every leaf on the tree before testing to see if any are valid. On the right, backtracking tests partial candidates as it builds them. Testing partial candidates gives the algorithm its defining mechanical advantage, pruning. The machine immediately drops an entire branch of the search tree the exact moment a constraint is violated. This 4-queen search tree shows a depth-first traversal. Look at the red node on the left. The second queen shares a column. This violates the constraint, killing the path immediately. The algorithm issues an undo command, retreating up the dashed line to start fresh. Translating that tree to a physical board, this cycle finds the single valid solution for a 4x4 grid. Modern implementations optimize this further. As shown on the right, the algorithm tracks safety using 3 mathematical hash sets, columns and both diagonals, allowing instantaneous constraint checks. By checking safety at the top of every loop, the algorithm turns an impossible maze into a systematic, self-correcting march. But there is a harsh mathematical reality here. The worst-case time complexity remains O of n factorial. Pruning offers 0 protection against adversarial inputs. However, space complexity is highly efficient, simply O of n. It only remembers the current recursion depth, not discarded boards. In Python, this logic hinges on a single load-bearing line of code. Before the recursion continues, an if statement checks whether the current column or diagonals are already occupied. If they are, the loop moves on. Equally critical is the cleanup step at the bottom of the block. Commands like remove or discard erase the last choice. This is the literal backtrack, wiping the slate clean so the next iteration starts fresh. By avoiding the memory overload of brute force enumeration, this compact loop allows standard laptops to solve combinatorial puzzles that would otherwise crush a supercomputer. Today, this exact logic runs silently in the background of everyday computing. It powers Sudoku solvers, parses complex regular expressions, maps maze routes, and generates data subsets. But you have to know its limits. If your problem has overlapping subproblems, you need dynamic programming. If local, immediate choices guarantee a global win, use a greedy algorithm. Backtracking is strictly for constraint satisfaction. To see the full code for these solvers, along with performance benchmarks, you can reference Imran Ahmad's 50 algorithms every programmer should know. Next time, we shift gears to algorithm number 13, breadth-first search, moving from diving deep to exploring wide. Backtracking proves a simple point. In computer science, knowing exactly when to abandon a bad idea is just as powerful as knowing where to start.